Hey folks, in this video we're going to discuss the derivative again and specifically how it relates to motion. Now there's a bunch of stuff written down on the page here. This is previous stuff. You might write it down again and have it in one spot. On the left side I've written the polynomial rule that we just discussed in the previous video. So if you can write y as a function of x such that y is a polynomial, y equals cx to the n, then the derivative of y with respect to x, and that's how you say this here. You say the derivative of y with respect to x, aka the slope of that graph, is equal to the coefficient becomes c times n, and the power of x becomes n minus 1. Okay. Now on the right side, I've written down our 5 equations of motion, and I'm going to talk about that as we go here. So the first 2 equations, the definition of average velocity and the definition of average acceleration, those are always true, okay? The last 3, though, are only true if, and that's why I have that big if written over there, if we have constant acceleration. So what we're going to talk about today is what if you don't have constant acceleration? Okay, so if you need a second to pause the video, now would be a good time and write that stuff down. Alrighty. So what do we do if we have a non-constant acceleration? Well, then if we have a non-constant acceleration, which by the way, a lot of motions are non-constant acceleration, constant acceleration is actually kind of semi-rare, actually. So if you have a non-constant acceleration, those last 3 equations, equations 3, 4, and 5, are null and void. You cannot use them. They will not be accurate. They will not give you proper answers. Okay. Now, the first 2 equations are always true. No matter what the object's doing, you can calculate its average velocity with equation 1 and its average acceleration with equation 2. There are 2 other equations that are always true, and I mentioned them briefly at the end of the previous video, and those are the following. Okay, velocity is always the derivative of position with respect to time. So another way to say that in verbiage is v equals dx dt. Similarly, acceleration is the derivative, the time derivative of velocity. It's dv dt, okay? So these 2 equations and these top 2 equations here are always true, okay? The other ones, only true if you have constant acceleration. So I'm going to kind of show you how this plays out in a fairly detailed example, okay? Now, by the way, constant acceleration, for instance, equation 4 here, if you have constant acceleration, the highest power of time you're going to have is t squared, okay? So let me give you an equation where there's a higher power of t, okay? So here it goes. Let's say I give you this crazy equation. So something is moving around. So here is its position with respect to time. 4t cubed minus 24t squared plus 20. And we'll assume that x is in meters and t is in seconds, okay, like normal. All right, so here's what we're going to do. We're going to calculate the velocity at 3 seconds, the velocity at 5 seconds. In other words, what would the slope of that graph be at 3 and 5 seconds? Slope is velocity on a position time graph. We're going to determine the acceleration at 5 seconds. We're going to determine a min and or max velocity as appropriate. We're going to determine a min and or max acceleration as appropriate. We're going to determine places when and where object turns around. In other words, let's say it's traveling to the right, and then momentarily after that, it's traveling to the left. When and where did it turn around at that moment? And then finally, we're going to find the average velocity between 3 and 5 seconds. Okay, so we got quite a few things to figure out here. All right, well, we'll start the very first one. And actually, I'm going to kind of talk about these three all together. How do you find velocity and acceleration if I've given you position as a function of time? Okay, well, velocity is the derivative with respect to time of position. So v as a function of time is dx dt. So we're going to use our polynomial rule to take the derivative of the position function as a function of time. So the first term, you take the 4 times the 3 and you get a 12, and you get t, and it's 3 minus 1, so it's t to the second, minus 24t squared. You take it 2 times 24, you get 48, and then it's t to the first, which I'll just write the t. And then the derivative of a constant, aka the slope of a constant, is 0. So technically you should have a plus 0 here, but I'm not going to bother writing that down. Okay. Now, from your velocity equation, how do you find acceleration? Well, acceleration as a function of time is dv dt. So I'm going to do the derivative again. So 12t squared becomes 24t, and then minus, and then 48t is 48t to the first. That becomes 48t to the 0, or just plain old 48. So now we know our velocity and acceleration as functions of time. Okay. Now, now we can start answering all these questions. So for instance, the velocity at 3 seconds, okay, you literally just plug in 3, okay, into your equation. So if I plug a 3 in here, 3 squared is 9, 12 times 9, then minus 48 times 3, it turns out, if you plug, you can check this in the calculator, but you should get negative 36 meters per second. And then if we plug in 5 seconds into this blue velocity equation, you get 12 times 5 squared minus 48 times 5. You should get, and again, you can double check this in the calculator, but you should get 60 meters per second. Okay. Now, I'll make a note. Well, I'll come back to it actually. All right. So we've answered the first two questions. What's the velocity at 3 seconds? What's the velocity at 5 seconds? So this and this are done. How about the acceleration at 5 seconds? Okay, well, that's easy enough. You just plug a 5 in for t in the red equation here, and you get 24 times 5 minus 48, and you would end up with a 72 meters per second per second. And again, if you want to check that in your calculator, that'd be good. Okay. Now, the next question, so we got this done. The next question asks for the min or max velocity, okay, as appropriate. All right, so I'm going to talk about this in two ways. If you are at a min or max velocity, in physics, we say your acceleration is 0, okay? In other words, you've reached a min or max velocity when you are done accelerating. Okay, so think about driving your car for a minute. If you're speeding up and then you reach your max velocity of whatever, 60 miles per hour, that means your acceleration at that point is 0. You're done accelerating, okay? Now, in math terms or in calculus terms, we say that you can figure out when the velocities are min or max by setting the derivative equal to 0. Well, what's the derivative of velocity? Well, that's acceleration. So in either case, you're setting the acceleration equal to 0. So to find when your velocity is a min or max, you're going to take the acceleration and you're going to set it equal to 0. And so you end up with 24t minus 48, which means t is 2. So at 2 seconds, your velocity is a min or max. Now let's figure out that velocity. So I'm going to plug 2 seconds into my velocity, my blue equation up there. The velocity at 2 seconds, if you take 12 times 2 squared, that's 48. And then minus 48 times 2 is 96. And you're going to get negative 48 meters per second. Okay. Now, that turns out to be a minimum velocity. There's a couple ways to figure that out. One way is to say, okay, if I look at the velocity at, let's say, 1 second or 3 seconds, is that number bigger or smaller than negative 48? And if you try that out, you're going to get a bigger number than negative 48. So this is a minimum velocity. Okay. Another way to do that is Well, there's other ways to do that in calculus. I'll let your calculus teachers talk about that. Well, I'll mention it. Another way is if you take the derivative of acceleration, okay? So if I took dA dt, this would be positive 24. So if that derivative is positive, it turns out that this is a minimum. And conversely, if dA dt happened to be negative, then this velocity would be a maximum, okay? But you don't really have to know that. You just have to know that, hey, I got to look at the velocity at some other moments right before, after 2 seconds, to kind of figure out what's going on, okay? Now, how about the acceleration, okay? Well, let's go back up, check our list. Okay, so yeah, we found the min or max velocity. How about the min or max acceleration? Well, okay, if you look at our acceleration function, it doesn't have a min or max. It's a line, okay? So the line goes off forever, down to the left and up and to the right. It's a positive slope line. Now, you could theoretically say, what's the min or max acceleration from time equals 0 onward, in which case your min acceleration, if I plug a 0 in here, would be negative 48. In other words, that graph, if I were to draw a little graph here of acceleration versus time, okay, it would start at negative 48 and it would go like that. So you could say, well, the min acceleration is negative 48, but technically that line keeps going, so there is no min or max, okay? Now, how about when does the object turn around, okay? Well, think about when you stop and turn around. What do you know at that moment? Well, you stopped. So you turn around when v equals 0. So what we're going to do is we're going to take our velocity equation, 12t squared minus 48t, we're going to set it equal to 0. So you got 0 equals 12t squared minus 48t, and then we can factor a 12t out, and you get t minus 4. So there are 2 times when this thing turns around, 0 seconds and 4 seconds, okay? Now, so that's when it turns around. Now, where it is at when it turns around, you would plug those 2 times into your original x equation, okay? And if you do that, x at 0 seconds is 20 meters, and x at 4 seconds is negative 108 meters, okay? So if you plug in 0 and 4 into that original x equation, those are the 2 numbers you're going to get, okay? Now, there's 2 more brief things I want to show you, okay? The next thing I asked you to find is what's the average velocity between 3 to 5 seconds, okay? Oops, let me rewrite that. Okay, well, if I go up here, I found the velocity at 3 and 5 seconds. It was negative 36 and 60, okay? If I do the average of those two, it'd be 60 plus negative 36, which would be 24, divided by 2 would be 12. So does that mean our average velocity is 12? Well, it turns out no. You can only use that equation if and only if you have constant acceleration. And we don't have that here. This is definitely not a matter of fact, here's the acceleration. It changes all the time. It's a line, okay? So it turns out the average velocity is not going to be 12. Well, how do you find the average velocity? Well, you do delta x over t, which is the x at 5 seconds minus the x at 3 seconds over time, okay? Now, if you plug in 5 seconds into your x equation, you get negative 80 meters. And if you plug in 3 seconds into your x equation, you get negative 88 meters, okay? And the time elapsed is 2 seconds, okay? So you end up with 8 over 2, which is 4 meters per second. So that's actually the average velocity between 3 and 5 seconds, okay? So that's, by the way, a common error that people make, is they'll try to average the velocity at 3 and 5 seconds, average those 2 numbers, and that's not correct for a problem that's not constant acceleration. For a problem that's not constant acceleration, you have to use the equation that always works, which is delta x over t, okay? And that will give you the correct answer. Now, finally, I want to make one more note. I went ahead and graphed this equation between negative 3 to 6 seconds for x versus t. That's the top graph you're seeing there, and then v versus t. Okay, so you'll see that we turn around at 0 and 4 seconds. At 0 seconds, we're at 20 meters from the from the origin. At 4 seconds, we're at negative 108 meters from the axis. Those are two turnaround points. This car or whatever this thing is going back and forth. Okay. The velocity graph is the derivative of the position graph, aka it's the slope of the position graph. So you'll notice between negative 3 and 0 seconds, the slope of the position graph in general is positive. That means these velocity values are all above 0. Okay, they're 60, 144, and 252. Okay, at 0 seconds, our slope is 0 momentarily on the position graph, and that means your velocity is 0. Between 1 second down to 4 seconds, your slope is negative. So those velocity values are all negative. They're all below the 0 t equals 0 axis, okay, or v equals 0 axis, okay. And then finally, for the last 2 seconds here, our position graph has a positive slope, and you'll notice those last two velocities are, again, positive. So that's the graphical relationship between position and velocity, between position and position's derivative. I hope that graph was helpful and broad, or hope that information was helpful, and hope that it also helped you with your calculus. Have a good one.